All right. So good morning, ladies and gentlemen. It's my great pleasure to start our inaugural conference. So now we pass to the scientific part after very kind and strong words about our project. And this is my great pleasure to introduce our first speaker, Jean-Stéphane Dhersin from University of Sorbonne, Paris Nord, who will talk on spatial evolution of an epidemic and social networks.
Thank you, Michael. I will present some results, and these results have been partially done with Anthony Cousien, Laurent de Cresfon, Pascal Moyal, Yeti Tran, and Feng-Thuy Vo. So, before speaking about my own result, I will speak about classic results, and the first one is SIR model for epidemics. Before that, I've been told that perhaps they would be a student in the audience, so I will give some probabilistic reminders about. The first one is about exponential variables. So I'm doing probability, so it's about probability. So the first reminder is we called T an exponential distribution. We say that T has an exponential distributor with parameter lambda if the probability density function is given by f of x is lambda e to the minus lambda x. So you can think about T as a clock, the time at which a clock rings, and the probability that this clock rings after time x is e to the minus lambda x. Of course, if T is exponential with parameter 1, you can give easily an exponential with parameter lambda by dividing it by lambda. And one thing which is very important is that these exponential random variables are memoryless random variables. That means that if the clocks, the probability that the clock rings after time x plus a, knowing that it rings after time a is the same as the probability that the clock rings after time x. It's easy to see. You have to divide e to the minus lambda x plus a by e to the minus lambda a. And now we will speak about the competition of these clocks. Suppose that T1, Tn are independent random variables, each with exponential rates B1, Bn, and so remember these are clocks, and you denote by T the mean of the T1, Tn, so the time at which the first clock rings. Writing that, and you assume that these clocks are independent. The probability that it rings after time t is the probability that all these clocks rings after time t, and this is e to the minus b1 plus b2 plus bn time t. So what we see is that the minimum of these clocks is still a random variable with exponential distribution, and the parameter is b1 plus b2 plus bn. And now one other question is which of these clocks rings first? So the probability that t equal t1, that means that the first one is the number 1, and we can compute and see that it is b1 divided by b1 plus b2 plus bn. So the probability of that the clock is the number I is proportional to bi. And last thing I want to remind is Poisson processes. So here the increments are exponential random variables with parameter 1, and you consider this process which jumps, the jumps are 1 at each time. So you have a first clock, and it rings. You jump. You jump here at 1, and another clock, and you jump, etc. So this process is called a standard Poisson process. This is also the number of clocks which have rank. If you change time, you can transform this standard Poisson process with another process with weight lambda. That means that these times are no more exponential with parameter 1, they are exponential with parameter lambda. And you can also, by this time change, have Poisson process with jumps with rate which depend on time. And if you give a positive function lambda t and change the time by the integral from 0 to t of lambda s ds, this new one jumps at rate lambda t. So now I will speak about epidemics. So you imagine that you have people in the population. The green ones are susceptible. They are susceptible to be infected. The red ones are infected or infectious. For me, it's the same thing. So as soon as you are infected, you are infectious. And the black ones are recovered. And how evolved the epidemic? Each infectious individual infects each susceptible individual at a certain rate Rn. So this one I cannot remove it. Okay. So this one can infect this one at rate Rn, and this one now is infected and infectious. So there is a total mixing. So there is no geography, or everyone can infect, the red ones can infect the green one at the same rate Rn, which depends on nothing. And in infectious individual recovered at a certain rate beta. So remember the clocks. You have clocks by pairs red-green. That means that when the clock rings, the red infects the green. And you have other clocks to recover on each red point. So you've seen this one at the bottom. Here is now recovered. And remember the infimum of the clocks, the exponential random variable is still a random variable, an exponential random variable with parameter the sum. So here, for each pair you have a rate Rn, and the number of pairs, red-green, is s to I. So at this rate, Rn times s times I, you have one individual from this compartment which goes to this compartment. You also have I clocks for recovering. Each one rings at rate beta. So you are going to this compartment at rate beta I. So the model is very simple. And this leads to Kermack and McHenrick equations. So if you consider this, during the small, suppose I'm a physicist, during the small time st, the variation of s is minus rsi times dt, and the same for the other one. So the equations are very simple. Now, if you are doing probability, what you observe is that you are going from this to this according to a Poisson process with rate which is rsi. So remember, you can change the time and you get you get this, and the same for the other one. So that is the evolution of the s, and that is the evolution of the I going from here to here. I just have subtract this quantity, which is in fact the expectation of this. And this is what is called the martingale. And now we have some equations. So this is random, this is random, this is random. Everything is random, in fact. And this is a notation for the expectation of the square of this quantity. And we can, of course, this is bounded by n, the total number of individuals in the population. This is bounded by n, so this is bounded by n squared times Rn times the size of the interval on which we have the integration. If we divide everything by n, so now we consider proportions. This is the proportion of S in the population, and this is the proportion of I in the population. What we get now is this equation, and this is still a martingale. And if we take this condition and Rn converge to R, this quantity will tend to 0 if we have this assumption beta n converge to B. We have this quantity tends to 0, and under some strong conditions, which is that the proportion at the beginning of the epidemic, the proportion of the people who are susceptible and the proportion of the people who are infected are not 0 nor 1. So under these conditions, you have a convergence, and the convergence is to the equation we have seen before. So at the end, at the beginning, everything is stochastic, but at the end, everything is deterministic. So this can describe the evolution of the epidemic when the epidemic has started and is really established. This is the condition S0 is not 0 nor 1, and I0 is not 0 nor 1. But one thing which is important is to know what is the evolution of the epidemic. So at the beginning of the epidemic, how does it work? For that, I have to give another reminder about the Galton-Watson processes. So this is, imagine that the dots are people in the population, and they have children. So this one has 3 children, and so on. So the number of children, the children are called offspring, and we assume that these offspring are stochastic, so not deterministic, and identically distributed. So the law of the number of children is the same all over the time. If the mean, so the average number of offspring per individual is smaller than 1 or equal than 1, then we have extinction almost surely. If m is strictly greater than 1, then with a non-zero probability, we have non-extinction. Now, I come back to the epidemic I have presented before with the compartment. At the beginning, suppose that only one individual is infected. You take one green individual in the population. What is the probability that this green individual is infected by the first red one at the beginning? It is infected if the clock red-green rings before the clock red to become recovered. And this probability, we have seen at the beginning, it is R divided by R plus beta for each green individual. So the probability that this given green individual is infected is R divided by R plus beta. We have n-1 individual in the population, green. So the law of the number of individuals which are infected is a binomial with parameter n-1 and R divided by R plus beta. And n is large, so this is loosely speaking this. And what we get is that this first individual infects this quantity of individuals in the population. And we have exactly a Galton-Watson. So the approximation is just, I have replaced n-1 by n. And we continue. And what we know is that this may explode if this mean, the mean of this, so n times R divided by R plus beta, is greater than 1. This is because R divided by n, Rn divided by n tends to R. This is equivalent to this. And we can see according to the parameters of infection and the parameters at which they recover, we can say when there is a risk of a major epidemic. Okay, that was without a spatial distribution, but in the real life, what we have people, of course, I have more chance to infect you because I am near you, that infect somebody, I don't know where in the US I have never met. So one thing which is more realistic is this SIR model on social network. So you still have this kind of individuals, susceptible, infectious, and recovered, and the vertices between the individuals means that you have relationships between these two individuals, and of course you can infect only somebody with whom you are in contact. And so you have seen this one will infect this one at a certain rate R, and you still have this rate beta at which you recover. Of course, the dynamic system is more complicated, and the question is, can we say anything which is relevant, and for which kind of graphs or networks? So a random graph is something like this, exactly what I said before, but without the colors. People are connected, and you can describe them by a matrix, meaning there is a 1 if, for example, this one means that the individual 1 is in relationships with individual 3. And one thing which I will use is degree. Degree is the number of your neighbors. For example, this one has degree 3 because he has 3 numbers, this one, and this one. So for the complete graph, in fact, the complete graph is a graph, the thing we have been before. Everything is related to everybody is related to everybody. Some well-known graphs are Erdős-Rényi. So here, the probability that you have an age is given by a probability, is given P, and it is the same for all the pairs. And we will see one example later, which is the configuration model. So what is the configuration model? You have n individuals in the population, and you want to construct a stochastic graph. So you have these n vertices, and what is easy to find in the population is the degree of each individual. So you ask the people, how many friends do you have? And so it's easy to have these degrees. And we assume that these degrees are random, but independent and identically distributed. So this one has two neighbors, and at the beginning you don't know who are these neighbors. Now you pair at random all these half edges. So you have this one, and you choose in the population of half edges one other half edge, and you pair them. Of course, sometimes you have something strange. For example, this one is connected to this one by this edge and this edge, so it's not allowed. And this one is connected by himself with this construction. So of course, at the, you don't have exactly a graph, because the graph is you have an edge or no, and you don't have an edge between you and you. But it is not very important, because we will consider n large, and with this thing, asymptotically, the number of multiple edges, like these two ones, or self-loops, like these two ones, is of order 1, and the number of, so it's negligible, and at the end, it is approximated by a graph. There are conditions for a giant exponent, because what I will consider is epidemic like this, on this, and of course, which is interesting is there a major, is it a major epidemic? So that means that at least of course, you can infect only somebody in your connect component. So you have you need large, giant components. So now remember, we have constructed on a given graph the evolution of epidemic here, and we have given a construction of the configuration model graph. And what we will consider is, so there are two origins of randomness, and what we will do is constructing the two things at the same time. So suppose that you know the subgraph where you have only the infectious and recovered, and you have half edges. To each half edge from the red one, you have a clock at rate R, and when it rings, you choose at random among all the half edges you have in the population, one of the half edge, one of the green, and this is the new edge. And this one has been contaminated. Okay. But perhaps that these half edges were already connected to people who were in the previous graph. So these half edges, you have to compute if they are connected to the red or the black or to the green. If they are connected to the green, they are still half edges, and if they are connected to the red or the black, you have to decide what half edges they are connected to. And you still have these clocks at rate beta to recover. For this one is recovered. So you have something. You have a new construction, and at the beginning you have only one. Remember, it's exactly the same as the comportmental model. And so I've written IT, so the number of red is much more smaller than ST, the number of green. And so here, assume it is 1. And so one of the half edges has a clock which rings. That means that it infects. So this one infects somebody. And you have to find one of all the half edges which are green in the population. So for each half edge, remember the degree distribution, so the number of half edges of a green one is given by a probability P. This one with 1, 2, 3, 4, 5 half edges are much more changed than this one, which has only 3 half edges, and of course this one can not be infected. So the probability that this one is chosen is the number of its alpha is proportional to the number of half edges. So there is a size by choice of the half edges, and the new probability is kpk divided by the sum. So it is normalized. So it is a probability distribution. And the number of, so assume that y is the time after which this one becomes recovered. The number of people you infect is, of course, the number of rings, of clocks that ring before this one rings. And it is exactly as the same at the beginning. So for which one it's 1 minus e to the minus ry, and we have k minus 1 alpha edges of this one. And you can compute this number of individuals, a given infected individuals will infect in the population. So if nu is the law, we can compute that it is exactly this. So it is exactly as before, a Galton-Watson process with some new offspring distribution which is given by this, and we can give some results about the R0, so the expectation of this one, and if R0 is strictly greater than 1, then you have a major epidemic. So for the complete graph, we recover this one, and we have also results for all what you want about on the distribution of the degrees. Now the second thing I have considered at the beginning is the evolution when the epidemic is established. Remember at the beginning it was only depending on the number of SI connections. So the time at the beginning for the comportmental model, where everybody is in the same group, it is the product S times I. Here it's different. Of course, the strength of infections is given by these alpha G's from the red ones. So here it's only 1, 2, 3, which can infect. So a relevant number is this number of edges from IT to ST, so this is the alpha G's from the red one. And if we denote by DI the degree of individual I, and DI of SD of ST the number of neighbors of individual I in ST, so here it is 2. And if we introduce some complicated distribution, so this, it's not really complicated. So it's only depend on the degree, which is the law of the alpha G's of the green ones. This is given by this is the distribution of the alpha G's from the red one, and there is also a distribution of the alpha G starting from the black one. What is the dynamic? So the rate at which you infect is R, which is for one alpha edge, times the number of alpha edges, and then, so this is the rate at which you have a new infection. And what is the probability that a given individual in the population, green, with degree K, this one, what is the probability that it is infected? To be infected, one of its alpha gene has to be chosen by the alpha edge which infects. So this is K divided by the total number of alpha gene you have in this population. So this is the rate at which a given green individual is infected. So now it is infected. After that, you have to compute how it is connected, and it is given by a certain probability. This explains how these these alpha G's are connected to the previous one of the subgraph. And one thing which is important is that you can describe, at the beginning you had 3 equations with the Poisson processes. Here you still have 3 stochastic differential equations, which are not so nice to write, so they are not written. But the thing you have to keep in mind is that it is exactly the same thing, but for measure value stochastic differential equations. And perhaps, so for the comportmental model, this equation was something like this. And here we can still write this evolution of the I using this measure distribution. At the end, you have something which is, I will not take time to explain this. The thing you have to keep in mind is that okay, it's not so nice as in the comportmental model, but for the configuration model, you still be able to write the equations, the stochastic equation for the evolution of the dynamics of the epidemic. And at the end, one thing is that, so remember, you at, okay, remember at the beginning, you had these stochastic equations, and you also have this deterministic equation, which were the limit of these stochastic equations. Here, so I will not explain the details, but what you have to see is that, okay, we have only 4, this one, this one, this one, and this one. This one is a consequence of this one, and this one. So you still have this kind of, in some sense, easy equations, which gives you the evolution of the population, and that's it.
Thank you very much, Jean-Stéphane.